Okay, so let me just to so we can catch up sometime, Adam, a little bit. So the topic is going to be harmonics. We talked about harmonics, guys, I believe also last semester a little bit. In terms of harmonic, your designers, electrical construction power designers. So our concern, Adam, is how would a harmonic load affect our branch circuits, feeders, and services? Um, Harmonic load is any piece of equipment, Karen, that has electronic equipment in it. Any electrical equipment that has, or appliances that has electronic equipment could be an offender when it comes to harmonics. In plain English, guys, harmonics are sloppy eaters of electricity, Matt. So what they do, the way they digest electricity, it screw up the power system. Okay, they don't digest it properly, and I'll show you what that means. So how are we concerned about it? Because it affects the design of our power system. And there's a couple of hints, guys, that you took into consideration when we designed your system that we're going to talk about in a second. Okay, a couple of things. Adam, we're going to describe harmonics. So we'll talk about what are harmonics and what do they do for a living. Then we're going to talk about, here's Derek. Good to see you. And we are going to discuss problems concerning harmonics. So what are harmonics first, and why do we care? The question, Adam, would be, see, why do we care about harmonic, right? There's harmonics, who cares? We're designers, right? Concerning problems concerning harmonics. Characteristics of different harmonics, so we can filter them and get rid of them. Bottom line, guys, plain English, we care about them because they screw up our power system. They overheat our neutrals, they overheat our circuit breakers, they overheat our transformers and circuit breakers and conductors, so they burn our equipment. So that's why we pay a lot of attention to them. Does it make sense? So that's what we're going to be talking about, guys. And then a couple of, obviously, there's a lot of tests that they use, perform tests to determine whether harmonic problem exists in your facility. Um, so Derek, with Parsons Electric, when they hire you as project manager, you walk into a place and they have a problem. What's their problem? The problem is their circuit breaker continuously tripping for no reason. So the first thing comes to your mind, I said, okay, do you guys have an overload condition? No. Do you have a short circuit condition? No. So, and they're still tripping. The second thing comes to your mind is, well, do you guys have harmonic problems? They said, what is that? Right? The customers, what is harmonic problem? So now we're going to talk about how do you do a test or determine if you have a harmonic problem in a second. Discuss methods of dealing. Then now we found that we have an evil. How do you deal with that evil that's called harmonics? Dealing with the harmonic problems. When you determine that you have a harmonic problem, how do you deal with it? Cool? Does that make sense, guys? Okay. So moving on into introduction. Harmonics. What are harmonics? Voltages. Harmonics, guys, are voltages and or current that are operate, look at the word, operate at frequencies in multiples of the fundamental frequency. You're going to see this one in a very second. So the frequency that we use in the US is 60 hertz. Here's my 60 hertz frequency, right? Can you see that? This is called the fundamentals. This is 60 hertz. Now, Derek, look what happened. If I have, this is what we love. Now, if you have a frequency that goes something like this, can you guys see that? Now, this is 120. Can you guys see that? This is 2 times 60 equal 120. So if you have a power signal that running at a signal like this, the bottom one, this is called harmonic, running at 120. We need the power signal, guys, to run at 60 hertz. If electronic equipment tend to screw up the frequency and make the power signal to run at other than the 60 hertz. So look at this. So instead of having one signal in 60, this is 60 cycles, 60 cycles in a second, you will have 120 cycles in a second, or multiples of 60. So 120, what else? 180, and keep multiplying the 60 by 1, 2, 3, 4. That's your harmonics. Who cares? It screws up the power system. It overheats things and causes problems. So it's multiples of fundamental frequency. Does that make sense, Derek? Multiples of fundamentals. Take the 60. 60 is what we love. That's called the fundamentals. That we love dearly. That's no harmonics in it. Multiplied by 2 becomes 120. You have a signal that running 120. That's a harmonic. So then add another 60, 180. Then another 60. And these are your harmonics that cause your problems. Why do they happen? They are caused by nonlinear loads. Nonlinear loads that draws current in pulses instead of rather than continuous. So that when you deliver, guys, we're in the business of delivering power, electrical power. When we deliver electrical power, Edison, God bless his heart, years ago, discovered we can deliver in DC, right? So here's my DC delivery. And that vehicle was great, awesome, until Mr. Tesla came and he said, I can deliver that power in a better means. You're driving that power using a truck, I can use an airplane to deliver, right? Or a train. So that's your DC. So then they escalated into what we call it the AC, and that's how it looks like, right? That's a superior. The AC, as we all know, has a lot of superiority characteristics over DC. So these are the two conduits of delivering power. When we were doing DC, we have no problem. When we start doing AC, if this is a signal that the current is pulling, you're good to go. Perfect, like motors and all these stuff and resistive loads and everything that doesn't have electronics. Now, when the electronic revolution start to happen, the semiconductors, guys, they don't, when they take a signal like this, you know what they do with it? They chew it. They made it look like this. The way they act, the way they react, the way they accept the electrical power, they screw up that signal. Now, to you and I, it doesn't matter. Two of the conductors in the transformer, that ripples, all these rough edges of the signal, that's heat generated in this equipment. Who cares? You either have to solve the problem harmonic by having filters, or you have to oversize your equipment so it can handle that heat. Does that make sense? So that's what the whole harmonic is, pulsation. So, and if you have PLCs, look at the PLCs. If you have VFDs, we were talking about VFDs. You know what VFDs do? Instead of giving the motors this signal to control the speed, they give them pulsation, guys. Something like this, you know. So, so they give them multiple pulsation like this. Look at this. Pulse. On, off. On, off. So by doing this pulsation, that you can control the speed of the motor, beautiful, VFD's advantage. But in the process, that creates a lot of distortion of the system, which means overheat the equipment. So who cares? We need to handle it, right? It's a necessary evil. It has to be there, but we need to handle it. Any question, guys, about harmonics? Nonlinear loads. A nonlinear load is any load that has any electronic device in it. Your laptop, this printer, show me anything that doesn't have an electronic device. That ballast, electronic ballast above your head, VFDs, soft starts, PLCs, all these that have any electronic device in it, semiconductors, will chew the circuit differently. So, Derek, every time you convert AC to DC, you create harmonic. Every time you speed control an equipment using a DC drive or an AC drive, you create a harmonic. Every time you put electronic ballast, which required by code now, you create a harmonic. So it's really necessary evil. You have to deal with them. We can't say, well, no, there's requirements how much harmonic you can generate by the industry. So you can't just generate unlimited harmonic. They limit the amount that you can generate by manufacturer. And the rest, we as a designer have to design a system to handle it. Okay, any comments, guys, about the harmonics? Does that make sense, Matt? Fundamentals of the frequency. Okay, so take this. This is a pulse width modulation, guys. What they do, they take an AC circuit here. Say, let's just say 480. I'm just going to use 480. They convert it to, say, 660 volt DC. This is an AC. And they invert it back at 480 with speed control. So they have a voltage regulator, speed control. So here's a transistor. It fires it. That's what we call it a pulsation. On, off. On, off. Who cares? This has got your speed control of a fan, speed control of the air handling unit. Big deal. Speed control of a conveyor. I mean, speed control, guys, in the mechanical equipment is huge. If you ever talk to mechanical engineers or manufacturing engineers, if they can speed control the equipment, if you have a conveyor that can you run it at 10 RPM, 20 RPM, 30 RPM with push a button, would you think that this will be, and you're making cars, wouldn't you think that's a huge advantage? You can control the process. So speed control is a big deal. So that's where the heart of harmonics started, where you take the AC to DC, you put them through the transistor electronics, and you invert them back to AC, you screw up the signal. You no longer have that beautiful signal that looks like this. Sinusoidal signal. Okay, so that's your offender. So because of this, here's what this is called the fundamental, which is the 60 hertz in the US that we use. Now, if you add harmonic to it, look what happened. If you add like second and third harmonic, I think this is second harmonic added to it. Look what happened to that beautiful signal. Or typical distorted harmonic. This is a voltage. Look what happened to the voltage. Look what happened to the current, right? So you bring a signal like this coming from Excel, beautiful signal, the voltage. Then you put it through a VFD. The output on the VFD, the voltage. Look at that. All these niches in it. That's bad news, right? And the current is even worse. The current's supposed to be the same, guys. Most part follow the same rhythm or phase shift or whatever. Look what happened to your current. Now this is supposed to be like this, and this is supposed to be like this. Just so you know. Who cares? This is a lot of heat in your equipment. A lot of heat in your equipment. So you have to handle it. Does that make sense, guys? Does that make sense? And if this is 60 hertz, this would be 60 hertz, 120 hertz, what else? 180 hertz, and a bunch of multiple of 60. Keep going to the multiple 60, right? So that's what harmonics can do to your signal. Okay, symptoms of harmonics. How do you know that you have a harmonics? Overheated. Can you even see the word overheated? Conductors and transformers. If your conductors are overheated and burning, the lugs are burning, especially in the neutral, and your transformer dies prematurely on you, that's an indication, and you're not overloading the transformer, the conductors, guys. That's an indication, Adam, that you have a harmonic problem. Okay? Circuit breaker tripping. Look at this. Circuit breaker that seems to trip for no reason. You guys go measure the current, and the current is beautiful. No overload in the circuit breaker, no shortcuts, no ground fault, and your circuit breaker continues to trip. Well, it could be a malfunction circuit breaker, or it could be you have a harmonic problem. Okay? Any comments, guys? Any questions about the symptoms? So it's easy. We'll talk about how you walk in and do a survey of your equipment. Okay, harmonics are classified. Classification of harmonics. That's on the test on Monday, Adam. We'll tell you how do you classify harmonics. Number one, name. The harmonics have a name. The first one, it's called second harmonic, third harmonic, fourth harmonic, fifth, sixth, seventh, eighth. And the first one is the first harmonic. First harmonic is called fundamental. The fundamental, that's a 60 hertz. Does that make sense, guys? First harmonic is a 60 hertz, which is the signal that we love. And second harmonic is, so the first, second, third, second harmonic, third, fourth. We start with the second because the first is the fundamental, the one that we love. So in terms of name, second, frequency, operating frequency. So the first, the fundamental, guys, goes to 60. This one goes to 100, 2 times 60 is 120. 3 times 60 is 180. 4 times 60, 4 times is 240. These are hertz. So the name is the second, the frequency is 120. The third, 180. The fourth, 250. The fifth, 5 times 60, 300, right? And so forth. That's the frequency that they run at. So that's your frequency. The second thing based on frequency. The third one is sequence. The sequence is, they go by 0, positive, negative sequence. 0, positive, negative. So they have 0, positive, negative, I believe. 0 has no effect no effect on the rotation of a motor. Positives make the motor run faster. Negative slows the motor. Does that make sense? 0, no effect on the motor rotation. If it's a positive harmonic, it makes the motor run faster. If it's negative harmonic, it makes the motor run slower. We're going to see that in a second. So harmonics, name, frequency, and sequence. Name, frequency, and sequence. Okay, harmonics called, there are a bunch of harmonics that are called triplens, guys. A special type of harmonic that are called triplens. Have a 0 sequence. These are zeros. 0 sequence, they start with a 0. And they are the odd multiples of the third harmonic. The odd multiples of the third harmonic. So I have third, ninth. What are the odd multiples of third harmonic? The odd multiples of 3. So 9, 15, right? Am I right? 15. These are called the third harmonic. 3 times 3 is 9. 2 times 3 is 6. We can't use 6 because we have to be odd. So 3, 4 times 3 is 12. We can use it. 5 times 3 is 15. Yup, it's an odd. Can I get you guys to understand that triplens have zero sequence, so basically they don't affect the motors, and they're odd multiples of the third harmonic. Okay, what do? Why are they so important? Those are the offenders when it comes to the neutral. Remember that when you go to Mashad, Adam, they will tell you, well, we're going to oversize the neutral because we have harmonic. Why? The main offender for harmonic on a neutral is the triplet. Because these guys, remember phase A, phase B, phase C in neutral? They're supposed to cancel each other. If they have 10 amp, 10 amp, 10 amp, you end up with a neutral 0 amp. You studied this one with basic electricity, right? When you guys did it. If you have harmonic, you have 10 amp, 10 amp, 10 amp, you'll have a 10 amp also on the neutral because of harmonics. So they screw up your harmonics. So we're connected to pulsation currents. Triplens, here's what they do. Disturb the normal, they call it normal phasor relationship between the currents and cause phase to add, that's the word, add the neutral to the neutral conductor. So you have phase A, phase B, phase C, 10, 10, 10. Instead of having 0 on the neutral, you get 10. Screw up the whole concept of three-phase system. The whole idea against three-phase system is you balance the loads, you get 0 on the neutral. Here you balance the load, you still get a full load on the neutral. Any comments, guys, about the triplet? You're going to hear about them all the time. Multiples, odd multiples of 3, basically. Third harmonic. Odd though, not even. So they'll give you the 3rd, the 9th, and the 15th, and keep going. And there's 0 sequence. Here's what they do. So Karen, if I have 100 amp here, and on this phase, and I have 100 amp here, and I have 100 amp here, in a normal situation, a neutral should carry 0 amps. Can you guys see that? Your neutral should carry 0 amp. If you have harmonics, your neutral could carry as high as 200 amps. Your neutral, guys, can carry twice as much as the phases. And that happens a lot in data centers. Derek, remember when we went to these PDUs? These PDUs, power distribution units, they size the neutral twice. They call it double neutral. They size the neutral twice as much as the phase. What the heck are you doing? Why would you do the neutral twice? Because of harmonics, because of the triplets. Can I get you guys to understand that one? Sometimes when you have triplets, which is the odd multiples of 3, they add up in the neutral and they screw up. You can have 100, 100, 100, should be 0. It adds up because of these into, go to the triplet, it adds up to 200 instead of canceling each other. Okay, so that's what they do to the neutral. Thermomagnetic circuit breakers. You have thermomagnetic circuit breakers, guys, which we talked about, that we'll be talking today too, like these ones. What they do is they are designed to respond to heat, right? They are thermal. Can you see the word thermal? The thermal part of it is designed to respond to the RMS current. Now, if you have more RMS current, what do you think the circuit breaker is going to do? If you have harmonics, you will have more RMS current. So the circuit breakers start tripping for no reason. So harmonic currents cause distortion to the RMS value. Who cares? Which means breaker trip when they shouldn't and or not trip when they should. Isn't that a bad idea? Imagine you have a circuit breaker that's supposed to trip if you have a ground fault on a short circuit, right? Or overload. Now it trips for no reason, and when you have certain things, typically more tripping. So it keeps tripping, nuisance tripping, drives the people nuts. So that's what harmonic can do to you. So what do? If you have a situation like this, you're going to oversize your circuit breakers, basically, compensate for the heat, divide the load between multiple circuit breakers. There's multiple solutions for this. Cool? So that's your thermomagnetic. Now, electronic circuit breaker, you're looking at it right here. By the way, here's a thermomagnetic circuit breaker. That's your thermomagnetic here. This is your electronic circuit breaker that we talked about yesterday. That guy responds to the peak value of the current. The peak value, if you have harmonics, is higher. It's typically higher than the sinusoidal wave. So again, it screws up to your calculation. So electronic circuit breaker, they're meant to compensate for that window. They can malfunction because of harmonics or nuisance tripping. Derek, does it make sense when you nuisance trip for these? So that's what it does. Look at this. Here's your sinusoidal wave, guys, the beautiful sinusoidal wave. You can see that's the one that we love, we can't live without. And then in between, you have multiple other harmonics. Look at the top, how the peak of the harmonic is higher. Can you see the gap? The peak of the harmonic is higher that will screw up the operation of electronic circuit breaker. Could screw up the operation of electronic circuit breakers. Any comments, guys? Any questions? Comments, questions? The fundamental versus a harmonic waveform. So all this is going to screw up your equipment. Okay, now what happened to the panel boards and ducts? Bus ducts, Adam. You have a bus duct like we did, or a panel board. Same thing, that triplen harmonic, that offender currents, cause problem with the neutral bus duct and the lugs. It heats the lugs, guys, in the bus duct, and the triplen heats the neutral if you have a neutral in the bus duct. And long story short, you have loose nuts and lugs inside the bus duct or the panels, and if you have loose connectors, guys, on lugs, what's going to happen? You're going to arc. So you got yourself an arc. Adam, a second thing, guys, can vibrate. Look at that. You walk into a bus duct and it's humming. The bus duct is humming and vibrating. So that's, Karen, that's an indication that you might have a harmonic problem. Cool. Also, to minimize interference, what they tell you to minimize interference with these, you group all your neutrals and conductors. So run cables far away from phase conductors and close to the neutral conductor. So to minimize, so when you, if you have a telecommunication cables, Karen, you move them away from the power conductors, so you don't have interference with them. All right, now. Adam, you have been hired to walk into this office and say, do you have a problem with harmonic or not? So determining the problem of harmonic, guys, on a single phase system. The first and the most important thing, Karen, that we do is we make an equipment checklist. List of all the electronic equipment in your building. Printers, laptops, electronic ballast, VFDs, soft starts, AC converters, all these have to have a list. So if you have them, then you could have a problem. Then, step number 2, review the maintenance record to see if you have a problem with breakers tripping. Do you have a problem with breaker tripping for no reason? Do you have a problem? Thermal imaging. Do you have certain lugs that's hot? Review the maintenance, because guys, facilities like Dunwoody and all facilities, they have to do an annual maintenance on these, annual or semi-annual, or every 2-3 years, every 5 years. You walked up, remember when we went to Allianz, how they were saying that every year they do thermal imaging of their equipment, and every 5 years they go on torque certain equipment. So it's not just throw the panel here and let it live for 50 years. You gotta keep maintaining it. So you look at the record and see if there's any tripping for no reason. That will give you an indication you have harmonic problem. Okay, 3, check the transformer. Check the transformer for overheating. Thermal imaging, go to your transformer. Is the transformer hot? Now there could be other reasons, guys, why transformers can't get hot. So these are just flags, flag 1, flag 2, flag 3. Add them all together, that will be an indication, oops, we have a harmonic problem. Now when you have a harmonic problem, what do? We'll know what we do. Any comments, guys, any questions about, this is single phase and 3 phase. This is your checklist. Here's a couple of things about meters, guys. If you in the industry, Derek, when you become a project manager, and believe it or not, you guys don't carry tools, but as an engineer, you go with electricians to investigate the situation because they want to hire you to solve it. So what happened is, make sure you look for a true RMS. This is called a true RMS meter. The meters that we have, guys, are the average meters or true RMS. True RMS, if you have a sine wave, it will give you a correct response. If you have a square wave, it also can measure it. And if you have a distorted wave, it also can measure it. So it's good for all types of signals. So if you have harmonic and you have a true RMS, if you look at your meter, did you guys buy meters when you were with us? Adam and everybody, you guys bought meters, right? The meters that you use, at the top it says true RMS, meaning go ahead, clamp it on, and it will read. It doesn't matter if you have distortion or not. If you have an average meter, the cheaper ones, look at that. If the signal is okay, like this one, no harmonic, it's correct. Now, if you start doing a square signal, like going to the output of the VFD, it will look at this. It will be 10% higher, so it's not accurate. If you have distorted large harmonics on it, look what it could be as much as 50% lower than what it should be. Does that make sense? So long story short, it gives you a wrong value. So they use them as an indication. Okay, so look at this. This is values are generally greater than the true RMS. So the average current values are generally greater than the true RMS in distorted signal. The average values larger if you have an average value on, here's my RMS value. I don't know why they put that one here. So the average value of a distorted signal is larger than RMS. I believe it should be right here. So the average value, so now if you're measuring, so if your meter is measuring the average value and your meter is not listed, it will get it down, it will get you a lower value here. Though the RMS value of a distorted signal will be higher. So long story short, that's why if you go back here, that's why you can see the distorted signal 50% lower. Your average, your meter will measure 50% lower than what it should be. 50% lower than what it should be. I think that's what they have. There's 50% lower right here than what it should be, where it should be right here. So it screwed up your data. Okay. So when you so determining if you have harmonic problems, here's what you need to do, guys. You take an RMS, can you guys see RMS value, go measure the current. Look what the current here, 36.8 amps. If you ever use an average meter, it gives you 24.5. Look at the difference from 36.8 to 24.8. So there's substantial difference. So long story short, what we're going to do, you're going to be doing, they use a method, guys, both average, one that can get you average, one can give you RMS, and they do a couple of calculations. In a second, you're going to see it. Problem of harmonic. Okay, in a three-phase system, how do you do in a three-phase system? Very easy. All the stuff that we did before, guys, applies to, meaning you have to have a list of all your electronic offenders, electronic equipment. You have to have a maintenance record, see what you did, right? Is that what we did? We have maintenance. So review the maintenance and check for transformers. So have a list, review the maintenance, and check for transformers. In addition to that, measure the phase current. So what you need to do is measure the first current in every phase, as well as a neutral. You measure an atom with a 2 RMS, and you measure it with an average RMS. And that will give you, if they're not the same, they'll get you a substantial difference that will tell you that you have a problem with your system. A true RMS and average RMS, if they're not closer in reading, it will get you that you have a problem, a harmonic problem. Guys, in this day and age, Derek, do you see that circuit breaker here has the capability of sending a signal to your laptop if you use the right controller on it and tell you exactly what the harmonic problem in your building and how much harmonic you have. So most of bigger building, guys, they don't even use this method. They use circuit breaker like this that monitor the system and tells you what type of harmonic. Not only that you have a problem, but also what harmonic. Is it the second harmonic, the third, the fourth, and how much? It's not enough to tell me I have a harmonic problem, but how much and which one is the offender? Is it the third harmonic, the fourth harmonic, the fifth, the ninth? Because if you know which one of them, Derek, and how much, if it's small, who cares? We can live with evil all the time. If it's the third harmonic and it's too big, then we might either have two solutions. Either we oversize equipment or we design a filter. A filter, guys, is a capacitor and a coil and a resistor, electronic device. They stick it into the system and it sucks that signal. So if it's 120 or 180, it just basically lock it and prevent it, filters it, doesn't allow it to go through. So that's why it's important to know not only that you have a problem, but what type of problem. In this day and age, like I said, you have your meters, digital multimeter will give you everything, a plus harmonic. Your circuit breaker can give you indication of harmonic. So most of the people now, guys, do it for with a meter. Okay, here's what look at this. Look at the reading of the RMS on the three-phase and neutral, and the reading of the average. You look at the substantial difference, 365 and 292, right? There's substantial difference. You can use these data to get you how severe your harmonic problem is. Dealing with harmonics. So how do you deal with harmonic? Again, quality experts. A lot of people, guys, I can't emphasize in this day and age, when we deal with harmonic, Karen, we have quality multimeter. If you have a multimeter, guys, it will give you a report about the kW, the amp, the voltage, the frequency, everything in your building, plus the harmonics. Which harmonic and what size. So it's a big deal. Then you don't know how to interpret it, you're going to give it to an expert, a power expert, and they will tell you, yep, based on these readings that we got, you have a problem with the fifth harmonic, and we're going to go plug a filter for you to cancel the fifth harmonic. So there are filters that they can add to the power system, guys, that can get rid of them if they're that severe. If they're not that severe, you can live with them by oversizing your equipment. Did you guys hear me? Either you oversize your equipment or you solve the problem by filters. Okay, in a three-phase four-wire system, remember that reduce the 60 part of the neutral, the offender, balancing, so you can, the triplens, you can balance your load. That's why, Adam, when you guys were circuiting phase A, phase B, phase C, you have to put, like, if you have 18 fixtures, you want to put them in a three-phase system. You put 8, 8, 8 on every phase. You shouldn't put, divide them 12 on one and the rest on the other two, because that will contribute to the triplens. Okay, triplens are present in the neutral conductor. You can put a harmonic filter at the load. If you have a triplen, you can put a filter, an electronic device that can suck these signals, frequencies, and does not allow them to destroy your system. So especially with the triplen, guys, the way we solve the triplen, a lot of engineering firms, Derek, they pull a neutral with every phase. So phase A, phase B, phase C, and neutral. So 6 conductors. That's one solution. The other solution is cut the load by half. So if the circuit is supposed to carry a 20 amp circuit, guys, supposed to continuously carry 16 amps. We load it to 8 amps. So if you have a problem with harmonic, no matter how high you can go the harmonic, you still don't overload your neutral. So cutting the load by half, gentlemen, pulling a neutral with every phase. These are solutions for the triplets in the neutral, for reducing the triplets in the neutral, or having a filter. We talked about here is pull extra neutral atom. So in a three-phase system, you have phase A, phase B, phase C, one conductor, one conductor, one conductor, and you have a neutral, one conductor, one conductor, one conductor. So for every neutral, for every phase, you have a conductor. Install larger conductor. You know how they do it? Some engineering firms, Adam, they go 3 conductors, number 10, or number 12, and 1 conductor, number 10, neutral. Do you guys see how they do them? The phases will be phase A, B, C, 10, and the neutral will be, the phases will be 12, and the neutral will be 10. Or they will have a neutral with every phase. These are what they use to get rid of harmonic, especially in lighting system and receptacles. If you guys remember in the commercial project, remember how the requirement was to pull a neutral with every phase? You hear this one all the time in engineering firms. That's to solve the problem of the triplens, the harmonics. Derate, reduce the amount of load. So the second thing is, like I said, a 20 amp circuit breaker, supposed to get you 16 amp continuous load, right? And instead of 16, I can go cut it down to 10 amps. I load it down to 10 instead of 16. We did that one, guys. When you guys with me, I was telling you that's how much we're going to load them. And you probably wondered why. It's Chad opinion. Taking into consideration, a lot of engineering firms don't load it except to 70% of the circuit instead of 80%, or 60% of the circuit. So they take, a lot of people say, okay, I'm not going to load my circuit except to 70% of the rating instead of 80%, or 60%. That's very common. So they reduce the load on the circuit. Who cares? You add extra circuits to handle that triplens. Okay, so transformer harmonic derating factor. The other thing when you have a harmonic, guys, almost done. You have a harmonic derating factor. They call it harmonic derating factor. This is method recommended by the computer and the business equipment manufacturers. Those are the offenders. Data centers. Those are the offenders. Those are the guys that. Do you guys remember the servers that we were looking at when we went to Allianz? These are, you talk about the offenders. These are the #1 offenders when it comes to harmonic. These are the ones who screw up your harmonic. So that's why we double the neutral. We add bigger loads for them than they need. So in order to, those guys also recommend to derate the factor. If you have a transformer, if you have a transformer Adam that can carry 100 kVA, if that transformer is feeding electronic, they derate it down to 70 kVA. Who cares? So instead of pulling 100 kVA out of a transformer, the manufacturers say, why don't you pull just 70% so you don't overheat it? Okay. So the way they do it, guys, they measure the following. They measure the amps. I'm going to show you in a second. They measure the RMS amps and the instantaneous peak amps. They do the instantaneous and the RMS, and they come up with a derating factor that looks like this. So do me a favor. Here's the values for your RMS. Can you guys see the RMS values for all your currents? Here's the values for the peak, instantaneous peak. You have a transformer and you measure the instantaneous peak. So what you do is you go measure the RMS as well as the peak. So you put your meter on peak and measure the peak and measure the RMS. Cool? And look what they do with this one, Karen. So they average them. So they measure them, and then they go here and they average them. Look at the RMS. I'm going to remind you. Here's RMS. Average them. So we averaged them. Here's the average for the 3 phases. Then they went to the peak and they averaged the peak. Here's the average for the peak. Here's my peak. Right? And then they plug it into this formula, gentlemen, which says use 1.414. This is the value multiplied by the RMS divided by the peak. And that will get you this derating factor. Who cares? If I have 1,000 kVA transformer, now that's my transformer, and I have a derating factor, so this will carry, then you take 1,000, multiply it by 0.722. Now this transformer is actually 722 kVA, so meaning you cannot pull out of this transformer without overheating that transformer more than 722 kVA. That's your derating factor. One more time, Karen, you measure all the RMS currents, average them. You measure all the peak currents, which is just put yourself on peak, average them, plug them into this formula. This is actually RMS, this is peak. Can you see that? Plug in, this is constant, C is a constant. And you get yourself that derating factor. Then when you put your load, don't put more load than 722 kVA. Does it make sense, guys? Okay, so that's your, so that's basically it in terms of harmonic. Any comments, any questions? The most important thing that we do, guys, when we have a harmonic, especially in data centers, when you have data center, you oversize things. Oversize, basically oversize. That's what the solution is. In a severe data center, they have a double neutral. The neutral will be double the phase, 100, 200. And they also have filters. These PDUs that you were looking at when we have pictures of PDUs right there. These PDUs, they have filters in them. They filter certain harmonics based on the equipment. And the filter, guys, goes by frequency. So you can have a filter for 120 hertz and a filter for 180, or a filter that can go multiple frequencies. So that's what they do. So, so overheating, so the harmonic will overheat your circuit breakers, and your neutral current will also be affected. You can overcome that problem by derating or reducing the amount of loads of the transformers or extra neutral connectors. Or if worse comes to worse, what do? You pull you have a filter. You have a filter for your system. Okay, let me see if I forgot something, guys, about our things here. So we got these, the offenders, we got the signals. I wanted to show you something here. Here's my neutral. We got that one, got these. Here's that meter that you can use for measurement, fluke, RMS and what's not. You know, you can, this is what you guys some of you are gonna be doing. Okay, this is what I would like you guys, remember the harmonics, this is important because remember that harmonics has a name. Can you guys see the name? And they have a frequency and they have a sequence. So 60 hertz, that's the fundamental. I'm sorry, it actually stopped positive, negative, 0. My apology. So we have 60. Then this is 60 times 2, basically times 2 will get you 20. So this is positive, negative, 0, and positive, negative, 0. Take it second, third, fourth, fifth. Can you guys see the frequency goes multiples of 60? And the sequence positive, negative, 0. If it's positive, when you put it in the motor, it will speed the motor. If it's negative, it slows down the motor. If it's 0, it has no effect on the motor except it will screw up the neutral. Your triplens, guys, here's your triplens. The offenders, the triplens, multiples, and here's your triplens. Basically, the triplens, which is multiples of 3. These are the offenders when it comes to the neutral. Karen, this on Monday will be on the test. They will tell you how do we classify harmonics. By name, by frequency, and by sequence. And how does the name? The name goes fundamental, which is basically the first here. Second, third, fourth, fifth, that's easy. How about the frequency? 60, then 60 times 2, 120, 60 times 3, 180, 60 times 4, 240 times 5, 300 times 6, and so forth. And then the sequence atom is always positive, positive, negative, positive, negative, 0. Positive, negative, 0, positive, negative, 0, positive, negative, 0, and keep going forever. What does that mean? The positive. What does a positive mean? It speeds the motor. What does the negative mean? Slows the motor down. What does the 0 mean? Has no effect on the speed of a motor. That's it. So that's basically that I wanted to show that one. We talked about these calculations that you do. Okay, so that's basically it. Any comments, gentlemen? Any questions? Comments, questions about harmonic? Sorry, I have to take care of this. So that will constitute, guys, the last basically class on the theory, and we did the calculation yesterday. So that's all what we have for you. I'm going to give you guys 10 minutes, and we'll go. We have until 9 o'clock, 9:30. What's his name is coming at 9:30. Guy here. He's going to be our speaker today. What's his name? My friend Guy here. He's going to be here at 9:30. So from what time is it now? Is it 8:30? Yeah, from 8:30 until 9:30, I'm going to walk you guys through the coordination. Cool? Thumbs up, chat. Good. Your spec is ready. We're going to hit the ground running. Tomorrow, guys, I don't have anything for you except I'm going to review for the test. And you have the whole full day to finalize. So you have plenty of time. Thank you.